Greetings, this is Mick McQuaid welcoming you to iste780 Data-Driven Knowledge Discovery, Day 15, the first video in which we will just discuss regression trees and classification trees and save some techniques for improving trees for later. So, what is a tree? What is a decision tree? Well, there's one right in front of you on the screen, and it illustrates not only what a decision tree is, but it also illustrates the main advantage of decision trees, which is that they're easy to interpret. So this is from the hitters data. This is baseball players, and the response variable here is the salary of the player. In this particular case, the salary has been transformed to the log of the salary. So where it says 5.11 actually corresponds to a salary of a little over $100,000 per year. 6.0 corresponds to about $400,000 per year, and 6.74 corresponds to a little over $800,000 per year. So what you can see are three leaves. The three numbers that I just mentioned represent the leaves of a tree. The very top of the tree is what's called the root, and it is traditional. Well, you must by this point in your computing education know that it is traditional to portray a tree as upside down with the root at the top and the leaves at the bottom. And the tree has branches, and so there are nodes at which the tree branches called internal nodes, and then the leaves are called terminal nodes. So we have three terminal nodes, and we have two internal nodes at which there are branches. One is at the root, and at the root we find the criteria for branching. This is a binary recursive tree, by the way. And at the root, we've branched on the basis of experience. And experience is in years, and it's in integer years. So the splitting is done at a midpoint between two integers, hence 4.5, even though 4.5 doesn't appear in the data set. So anybody whose experience in years is 1, 2, 3, or 4 goes down the left branch. And anyone whose experience is 5 or more goes down the right branch. So what this is telling us is that years of experience is the most important determiner of salary. Then second, if you have experience, if you are if we know nothing about you at all, by the way, years are what's most important. If we know that you have been in the major league for a certain period of time, though, then hits become more important. So if you have fewer than 118 hits, really, you go down the left branch of that subtree, and if you have 118 or more, you go down the right branch of the subtree. So the prediction that we make for each terminal node is the mean of the salaries of the players at that node. And so there are plenty of players in each of these nodes, and there's quite a bit of variability in their salaries. But these are the predictions that we're making. This is what a recursive binary tree allows us to do. This is as good as it gets, and in fact, the predictive power of a tree is not very great. Its great asset is in its predictability. Now, as you may guess, recursive binary splitting can lead to a rather large tree. And this is another picture of the same tree, by the way, that we just looked at, with observations in here based on years and hits. So the space has been divided up. First, the space was divided on years, so a line is drawn through the data here. Then for everyone on this side of that line, a line is drawn through here like this. Now that's very important, because it indicates the kind of geometric shape that's possible using a recursive binary splitting. So we'll take a look at another example of that in a second here, if I can ever find it. Of course, I can't fit it all on one screen here. Let me, why can't I shrink this? can't seem to shrink my display here. This is really odd. I don't know why that is. But in any case, what we see here, here's a tree. Here's an example of a tree. Here's a geometric representation of that tree. This is a representation that you could never get using recursive binary splitting. So let's look at how this geometric representation corresponds to this tree. So the first split was T1. So we have split this box by this line. We've taken this box that I'm tracing here and split it at this line. Then we take a box, the box with the most variability, split it at this line. Then we take the box with the most variability, which is this box now, split it at this line. Then we take the box with the most variability, it's this one, and we split it at this line. So you can see that this wouldn't be possible. These lines wouldn't be physically possible on the basis of this. And then this is just a perspective plot of the prediction surface corresponding to this tree. Now, as I said, this tree can grow quite large. Let's look at a more full one. And gosh darn it, I just can't seem, there's something wrong here. I'm just going to pause this and see if I can figure out how to fix this. So as soon as I paused it, I was able to fix it. Okay, so here is a more extensive picture of the hitters data. So here's the first branch that we took, years less than 4.5, and the second one we took hits less than 117.5. And now we have a whole bunch of others. So we now have a complete regression tree. And you can do a regression tree with a cutoff. Either a cutoff could be some number of leaves. It could be some fraction in each leaf, some fraction of the observations in each leaf. It could be a cutoff of RSS or MSE. So there could be various cutoffs. But anyway, this is a complete example. Now you'll notice it says in the caption that it's an unpruned tree and that it results from top-down greedy splitting. So what we do in this, let me just make sure we know what we mean by the terms top-down and greedy. So we start with all the observations and then we split them on the basis of what reduces RSS the most. So we make that split. Then we find which of these two we can use to reduce RSS the most, and in that one we make a split. And so that's top down in that it starts with all of the observations and goes to smaller and smaller groups of observations. So that's the sense in which it's top down, and it's greedy in that we take the decision that's immediately the best, that results in the immediate biggest reduction in whatever it is that we're trying to reduce, in this case RSS, but it could be anything. And that's greedy. So we don't look ahead. We don't realize that there might be a few steps away that's better than this. So we don't take. There's no backtracking involved in this. So that's what we mean by a greedy algorithm. Now, this is not very good, and it can quickly grow extremely large. So we would like some way to prune it. And in fact, if we prune this tree, we're going to find that we can get a much better tree through cross-validation. So, and here's an example of cross-validation. But let me just go back to what it is that we're going to do to prune the tree. So we're going to build this tree. So we're gonna build this tree when and stop when each terminal node has, for example, some fewer than some minimum number of observations. That doesn't necessarily have to be the stopping criteria, but that's our stopping criteria. Then we're going to apply something called cost complexity pruning to the large tree in order to obtain a sequence of best subtrees as a function of alpha. Okay, and that means that we're going to minimize this quantity, and this should look very familiar. This is just the same thing that we did, or an analogous thing that we did with the lasso. So here we have the size of the terminal node, the number of terminal nodes of a tree. R sub m is the rectangle corresponding to the mth terminal node. Y hat sub r sub m is the predicted response associated with r sub m. So that is the mean of the training observations in r sub m. So this is exactly the kind of thing we want to do, is minimize this, but we don't want to overfit. The more terminal nodes we have, the more we'll overfit. So the larger we make this penalty, the larger we make alpha, this penalty, the more there will be penalized for having lots of terminal nodes. And this can result in a nested model so that it's easy to track our way through it. And this is exactly what happens here. So now it's a function of alpha. The MSE is a function of alpha, but it's being portrayed here as if it's a function of the number of terminal nodes in this tree. Okay, and so what you can see is that the minimum cross-validation error, which is the green line here, happens at a size of 3, which is the very first picture we looked at. The picture that just split on 2 criteria, first years and then hits. That's actually the best as far as cross-validation is concerned. Now, it turns out that it's not the absolute best according to the test MSE, but it's quite close to the test MSE, and it is a very parsimonious model. So it's a pretty good, pretty easy to interpret model. It makes a lot of sense. Okay, now I skipped a couple of little things here. One was this equation here. So we want to minimize this. Oh, I skipped this equation too. This is the boxes that minimize the RSS given by this equation, or this expression, I should say. And of course, it is computationally infeasible to do this. So this top-down greedy approach of recursive binary splitting deals with that fact by simply taking the best path as it appears at each given step. Okay, I think that pretty well covers that. It certainly does not absolve you from reading over this, but that's kind of the high points of regression trees. Let's take a look quickly at the high points of classification trees. So classification trees, very similar. The only difference is that we can't use RSS as a criterion for making the binary split, so we've got to find something else. And that's a little bit tricky. So you might think the classification error rate is a good idea because we've done that before and it's worked before. It's not going to work as well in this case. And here are a couple of better alternatives to the classification error rate. One is called the Gini index. Now, I should point out that there's a completely different concept also called the Gini index that has nothing at all to do with this. So if you happen to look for that, if you happen to Google for Gini index, you are quite possibly going to find something completely different here. And then also this is called cross entropy. I learned this just as entropy. The textbooks that I've used in the past have said entropy, not cross entropy, but this is a very common concept under the name entropy. And both concepts work roughly the same way, and they depend very much on this quantity, p hat sub mk, the proportion of training observations in the mth region that are from the kth class. So this is the fraction between 0 and 1 of training observations that go in one of these boxes that are in class K. And what's going to happen is that number is you can think of that number as taking on it can take on any values between 0 and 1, but you can think of it taking on 3 kinds of values: values near 0, values that are more in the middle, and values near 1. And what we would like to do is have a measure that's small for values that are either near 0 or near 1, and are large for ones that are in the middle. So both of these manage that. So in this case, if this is close to 1, then this will be close to 0, and the whole quantity will be quite small. 1 minus this is obviously close to 0 if this is close to 1. If this is close to 0, we're multiplying, something close to 0 by this, so that the fact that this is close to 0 is going to overwhelm this and make this a small number. If it's close to 1, this is going to overwhelm this and make it a small number. The same thing is true here, although it may not be quite as obvious. So because this is between 0 and 1, and because of the shape of logarithms, this number is going to be, by itself, is going to be a negative number from 0 to minus infinity. So as this approaches 0, this is going to approach minus infinity, but it isn't going to matter because the fact that this is 0 is overwhelming it. If this is close to 1, this number is close to 1, this number will be close to 0. And so minus this times this, which is a negative number, will be a small positive number, which is what it says here. Okay, so because this is always less than or equal to 1, this is always going to be 0 or a negative number. So in any event, this is this is a good statement of it. Like the Gini index, cross entropy will take on a small value if the mth node is pure. That is, if a node contains predominantly observations from a single class. Okay, and in classification tree, that's what we want. All right, so that's pretty much it for the classification tree. Here's an example of a classification tree. This is with heart rate data, or not heart rate, heart disease data. And the question here is, the response variable is, does the patient have heart disease or not? And then there are a bunch of variables. There are several dozen variables that are that have been recorded about them, and there are several that turn out to be important. So where is the cross validation minimized? I'm sort of not really seeing it here. Let me just enlarge this. Oh, okay, right here. So it looks to me like that's 6. And that's what we've got here, 6. So maximum heart rate. So these are patients who showed up with chest pain. I'm not sure why chest pain is in here. These are patients who showed up with chest pain, and these measurements were taken, and then they either have heart disease or not. And so maximum heart rate, I don't know what CA is. And chest pain here doesn't mean the existence of chest pain, because everyone in the group has chest pain. So it's some function of chest pain. And I don't know what. Oh, okay, I see. So chest pain is one of these categories. This is a categorical variable: typical angina, atypical angina, non-anginal pain, and asymptomatic. Okay, so in any event, this is just an example of a classification tree. Now the question is, why would you ever want to use these trees instead of linear models? So here's a linear model. Here's a regression tree. Here's an example of 2 problems, one of which, here's a problem where a linear model works better. Here's a problem where a regression tree works better. the decision, I mean not a regression tree, a classification tree. This is classification, right? Yeah. So in this case, the decision boundary is very well modeled by a line. The decision boundary is between these two classes, the yellow class and the green class, and the classification tree has a very tough time with this. This is as well as it can manage on this. Here, the classification tree has a very easy time. The linear model has a tough time. This is the best the linear model can manage. So, and again, this is a cooked example like something of the others, but it just illustrates that there are cases where one model dominates the other. And of course, as is typically the case, the only way that you know that is if you know the answer, which you don't know. So you have to have these models available to you and ready to go for different kinds of data, and sort of milk the subject matter experts for all they're worth to try to figure out which model is likely to work better on a particular kind of data. Now, speaking of subject matter experts, quite a lot of subject matter experts are not regression experts. So you can explain a tree to them. That's really it. In my view, that's the only reason to use trees, is they're easier to explain. People say that they mirror human decision-making. There has been a lot of research on that, but that basically, all that says is that they're easy to explain to people, in my opinion. They can be displayed graphically. As far as I'm concerned, that means they're easy to explain to people. This isn't so significant in my mind, that they can easily handle qualitative predictors without the need to create dummy variables. Dummy variables aren't really a problem. We can load up dummy variables, and so I think this is a fake advantage. Now there is a lack of predictive accuracy. This is the problem, lack of predictive accuracy. They may be non-robust. A small change in the data can cause a large change in the final estimated tree. I'm not sure that that's as important of a problem as the fact that they lack predictive accuracy. So really they're primarily used where interpretability is the most important criteria. Now, in the next video or videos, we're going to look at some techniques for improving the performance of trees so that we can use trees without suffering at least as much predictive accuracy. I mean, there may be cases where you're going to use a tree anyway, so you may as well try to squeeze as much out of it as you possibly can. All right, that's it for just the plain vanilla trees. Thanks for your attention, and I look forward to talking to you about bagging, random forests, and boosting.